Hi everybody, welcome back to the Feynman Technique. Here's another integral from Maths 505. We're going to be using some tools today. Basically this one, this sum right here is equal to the natural log of 2. This one is equal to pi squared over 12. And these two expressions are equivalent on that interval. I've gone over most of this stuff on my channel already, so we'll just take that for granted. So let's get started on the integral. All right, oftentimes when trying to solve an integral using Feynman's technique, if you see a natural log x in the integrand anywhere, that's a big clue that your reparameterization is going to involve x to the t. Because when you take the derivative with respect to t of x to the t, you recover a natural log x. All right, so keeping that in mind, let's make the following reparameterization. Let's make f of t a function equal to the integral from 0 to 1 of x to the t times the natural log of x plus 1 dx. All right, well that doesn't help us directly, but if we took a derivative with respect to t, we'd get f prime of t, and you use the Leibniz rule for differentiation under the integral sign here. That would be x to the t, natural log x plus 1 dx. And we will notice that f prime evaluated at the point t is equal to 0 will give us back our original integral. All right, so now the next step is to find a different representation for our f of t. We'll be using this right here. We'll be replacing this natural log of x plus 1 with this sum. So let's go ahead and do this. We'll call this new representation, we'll call it f expressed as a sum of t. So f sub s of t. And that's going to be equal to, well, let's see. Let's just rewrite this, but replace this with this. So we're still going to have the integral from 0 to 1. We'll have x to the t, but in place of the natural log of x plus 1, we'll have this sum right here. So we'll bring out the negative sign. We'll have the sum going from 0 to infinity of negative 1 to the n times x to the n over n dx. All right. We can bring this x to the t inside the sum by just calling this x to the n plus t. All right, we can use Fubini's theorem to switch the integration and summation notations there. So let's do that. We'll have the sum going from n equals 0 to infinity on the outside. And then we'll also have an integral going from 0 to 1. All right, we'll take this negative 1 to the n outside of our integration because it does not depend on x. We'll also take this 1 over n outside of our integration because it does not depend on x. So this simply becomes the integral from 0 to 1 of x to the n plus t, which is going to be 1 over n plus t plus 1. So we can just put n plus t plus 1. And that's it. There is our function of t expressed as an infinite sum. All right. Well, that's not a useful function for us, but its derivative is. So let's go ahead and take a derivative with respect to t of this. And that's pretty straightforward. You literally just take the derivative with respect to t of the integrand right there. So that means that our f prime expressed as a sum in terms of t is equal to, well, let's see. The only part that depends on t is this 1 over n plus t plus 1. Taking its derivative with respect to t will give us a negative sign, canceling with that negative sign. So we'll still have the sum as n goes from 0 to infinity. Let's see, we got rid of the negative sign. We'll still have this negative 1 to the n, but this will be now over n times n plus t plus 1 all squared. All right, so there's our f prime expressed as a sum in terms of t. All right, well, now we just plug in 0 and we have I. All right, so let's write that down right here. So that means that I is equal to the sum as n goes from 0 to infinity of negative 1 to the n over n times n plus 1 all squared. All right, and a lot of times I would leave it like that because, you know, I like infinite sums. I think they're perfectly acceptable representations for, you know, answers to integrals, because you can approximate the true answer to that integral very easy just by adding up, you know, just adding up the sums in that sum, just adding the terms together. And the first 10 terms would get you a pretty close approximation. All right. And that would totally be doable by hand. But in this case, we can actually break this up. So we could use partial fractions on 1 over n times n plus 1 squared, but let's do it, let's be a little bit more clever. All right, so let's start with 1 over n times n plus 1 all squared. Well, we could add an n to the top right here, but that means we would have to subtract 1 over n plus 1 all squared, right? Yeah, that's true. All right, so this would just become 1 over n times n plus 1. So this is the equivalent to 1 over n times n plus 1 squared. All right, but we can do a little bit better. We can add another n. All right, so what did that do? Well, now we're going to have to subtract 1 over n plus 1, and this will just become a 1 over n. And I think that's a lot easier than partial fractions. And there's a lot of times you can break them up using that method. All right, so that means we can rewrite this as, just put right there, equals. This is going to be equal to the sum I think I must have done something wrong here. I did do something wrong. Right here, you'll notice that this sum actually starts at 1. So, there we go. 1. Not that big a mistake. It was about to make it so that one of my sums didn't converge, though. If that started at 0, and we did the sum from n equals 0 to infinity of this thing, I mean, 1 over 0 is infinity, so, I mean, that wouldn't really work out very well. So it's important to remember that in this equivalency, the n has to start at 1. All right. Okay, so what now? Well, let's just rewrite this sum using the 3 separate fractions that we got by decomposing this one. So that's going to be the sum as n goes from 1 to infinity of negative 1. We can't forget that negative 1 to the n. That applies to all of the numerators here. Negative 1 to the n over n. And that should be familiar. That's the alternating sum. That's the alternating harmonic series, which converges to natural log 2, as we showed right there. All right, and then that's going to be minus the sum as n goes from 1 to infinity of 1 over n plus 1 squared. And you should recognize that one too. Well, that's this, basically written in another form, almost. Okay. All right, well, let's just keep going. All right, so minus the sum as n goes from 1 to infinity of 1 over n plus 1. And these are all negative 1 to the n's. All right, so that is going to be our I. All right, so let's see if we can make this stuff match this. All right. Well, let's make this index start at 0. So that means I have to add 1 to all of my n values inside it. So that would still be true. Okay. So now you'll notice we have this and we have this. They don't start at the same n, though. So let's change the index on this, but we'll do it in a different way. Instead of adding 1 to the index here, we're just going to subtract the 0th term. So what would that be? Well, let's see. If we plugged in n equals 0, this would become a 1 over 1, or minus 1. So we really, by changing the index, we subtracted 1. So now we need to add it back. All right, and now you'll notice that this and this are exactly the same thing. So we can just put a little 2 there and erase this entire first part. All right, and now we've got something pretty useful. Let's see, this almost matches up with this, except we have n starting at 0. So let's make n start at 0. All right, so we've just added the n equals 0 term. What is the n equals 0 term? Let's see, this would become a 1, this would become a 1, that would become a minus 1. So we subtracted 1, so we need to add another 1. So there we go. All right, well, now we have this matching this exactly. All right, so this whole expression right here, including the negative sign, becomes a negative pi squared over 12. And this, well, let's see. This is, the sum is n equals 0 to infinity of negative 1 to the n over n plus 1 is equal to natural log 2. So we have minus 2 natural log 2, and then plus 2. So all together, this is equal to 2 minus 2 natural log 2 minus pi squared over 12. And I really hope I got that right and didn't make any mistakes. I don't think I did. Of course, you'll never know if I did because I won't post the video. So anyway, there you go. This right here is the answer to that integral, and I hope you enjoyed that.